The organizers for allowing me to speak here. This talk has to be a review on the subject, so I'm going to report on several work people have done in the last few years. Alright, so very quickly, just to summarize what the freeform is. So it's a total antisymmetric tensor. Yeah, we know that, we experienced that. So when we do calculations with cross product, right? So the Lagrange symbol is defined, or cross product defines the freeform. And why should we work on that? Because until recently, we didn't know any scalar field. The only scalar field we know now is the Higgs field. And it makes sense to look for alternatives to the scalar field. And besides that, when we work with vectors, people do work with vectors, or two forms. The three forms are special because they treat spatial coordinates in a democratic form. Okay? So they support isotropy. And they do exist in string theory. Particle physics. Right, so this is where we start from. So this from this action, we write the stress tensor this way as an equation of motion, and due to the symmetries of these tensors, we have this constraint equation. Okay, and you can rewrite this in a different way. Before I go there, there's a group of relations between these forms: the three form, the four form, the vectors, and the scalars. And we can do this. We can write Lagrangians for all of these, yeah, and they are all equivalent because you go to the dual of the three form, which is a vector, and more explicitly, we can have these relations between the forms and the vectors and the scalar. It's the way you formulate the theory, which is in this three form, in a Faraday description. That's what the F means. This Faraday formulation. Then you can go to a four form, doing this divergency, actually. Doing a gradient of the three form, you get the four form. Yeah, you can do the dual and go to the vector. You can write the vector as a gradient of a scalar and go to the scalar formulation. Okay, to different formulas, you go from one to the other. So this is a nice description of how we go from one to the other. All right. So what is important for us is the cosmology. So we're going to focus on the FRW, and we can write three form. The background like this, the Lagrange symbol and the scalar field. Okay, it's a degree of freedom. That's what it means. And the equation of motion looks like this. It looks very similar to the equation of motion of a scalar field, but it has this extra term, which is going to do funny stuff. Yeah? And for the matter fields, it's the same equation of motion. Right. So the Friedmann equation reads like this. The only different thing is the kinetic energy. And if we realize that the chi dot is h chi prime, where prime is d divided by A, then you can rewrite the Friedmann equation in this way. Okay? So this is something that I want you to remember, because we'll come back to this in a second. And you can write the equation of motion like this. You can realize that if there is no potential, we get a cosmological constant. If this quantity here is negative, then you have a phantom behavior. Okay? Right. So we can write this system as a system of first order differential equations, obtain the fixed points, and what you get is these fixed points. Yeah? But the funny one is this one, and I'll try to motivate how you get this one. Okay? So going back to the Friedmann equation, which I asked you to remember. Yeah? So you have this, and you can understand that h squared must be positive, which means that this has to be smaller than 1. Right? So imagine that for this potential, we started in a very large value of chi. Yeah? So this could only be possible if chi prime, the velocity was negative to compensate for the large value of chi. Yeah? So with a setup like this, the field would have to go inside. You see, you have to go to 0. Yeah. Now the other way, if you are in this with this small value of time, or very close to square root of 2/3, then the velocity has to go to 0. Okay. So it means that you can always enter this region here, defined by square root of 2/3, which is about 0.8, but you can never get out of this region. Yeah? Usually I joke with this and I say it's like the mafia. You can get in, but you cannot get out. Okay, so this is, for this potential, we have some behavior like this, and the fluid will come down to the minimum of the potential. Now, if the potential is upside down, something like this, so remember, the field can go inside, but it can never go out. So the field will be stuck in between this barrier and the negative slope of the potential. Okay, and this brings interesting behavior, which is very different from the usual scalar field. So for a potential like this, yeah, we have the effective potential like this. Yeah? So we have a critical point here, but the field would remain here. Yeah? Would climb up the effective potential and stay stabilized here. Okay? And in terms of the field and energy densities, the field comes from a large value, turn around, and inflate for a long time, near square root of 2/3, and then come down and oscillate at the minimum of the potential. Okay? And you see that the equation of state is well defined, goes from 1 to -1, say a long time -1, and then oscillates around 0. Okay?
So you're ignoring quantum fluctuation through the zero. It's actually a diffusion process, not just a drift.
So you mean at the minimum?
No, at the potential. You will have fluctuations.
Yes.
Due to the jitter.
Yes. Yes. We will use it for inflation. Yeah. Right. So you can define this, how long this epoch of tracking lasts for, when turnaround happens. But the important thing here for inflation, in a second, is that inflation lasts longer if the initial value of chi is close to this square root of 2/3. So it stays there a long time, and then it goes away and settles in the minimum. So I think this is interesting for several reasons. Maybe I take some time to say this. It's interesting because we can have inflation with the small value of the field. Yeah, not for standard inflation phi square, say that the field has to be a 3 Planck mass. This has to be smaller than Planck mass. Yeah? And the only requirement is that longer inflation means you have to be closer to square root of 2/3, but it never goes above Planck mass. I've seen is that this setup naturally sets initial conditions for inflation. Because the field comes from a large value, yeah, goes to 0, goes to square root of 2/3, stays there a long time. Okay, so you don't have to put the field up in the upper position. Yeah, it naturally is left there. Okay, and so thereby the matter field. Right, let's move on. So for another potential, for this potential here, depending on the value of c, if it's large or small than square root of 2/3. The dynamics would be different. For in this case, the field would settle at this minimum, this one, and in this case, it would settle in this minimum here. The minimum effective potential, which is again between the slope of the potential and this barrier square root of 2/3. Okay, so I'll move faster now. This matter. The point is, you can have, because of these solutions, you can have viable models of dark energy and inflation a priori. I'm going to look at this more closely. So first example is inflation, yeah? And we have to work out the perturbations, and you can find the second order action for the tree form, and you identify the speed of sound being this ratio, written in terms of derivatives of the potential. Okay? And then you can work out the power spectrum, and you see that this looks the same as the P of X theory, like K inflation. Okay? So there's the speed of sound there. It's the only thing that changes with respect to the standard scalar field. And spectral index looks like this. Because tensors do not couple with matter in linear order, then it's a usual expression. The usual expressions for the power of the spectrum. And the ratio of tensor to scalar perturbations looks like this, like for the PFX series. Yeah? And for a third order, in order to calculate the bispectrum, then you can identify this quantity lambda in this way. Again, in terms of ratio of derivatives of the potential. Okay, so this is very clear. Alright, so here more explicitly, if we start with a potential like this for the tree form, you can write it as a P of X theory with a quadratic potential. Okay, and because it's a quadratic potential in slow road limit, then what matters is really the quadratic potential. So we see that spectral index is very close to what you'd expect for a quadratic potential in the scalar field model. Okay. And okay, these are the limits from, I think it's 2013. So there's a region of parameters that fits the data, and the dominant amplitude is in a equilateral shape. Okay. Right. So this is another example of a potential. It's exponential now, and you see, even though we have this relation between this free form and scalars, it's a formal relation. In practice, you cannot always do it, yeah, because you cannot always invert the potential and write it in terms of the kinetic energy of a scalar field. So for this example, which is very simple potential for the free form, it's complicated in terms of a scalar field. Yeah, it's a Lambert W function here. So in cases where you have, for example, a polynomial form in the free form, you cannot invert it and write it in terms of a scalar field. So it's good. It's a good thing to write everything from the start in terms of the free form. So in that sense, they are different descriptions. Okay. Right. So once again, because we have a quadratic potential here, then the spectral index is very close to what we obtain for a scalar field. This model does not satisfy the bounds on the non-Gaussianity, though also the dominant shape is the equilateral one. Okay. Right. Then we looked with Shravan Kumar at multi-field models of free forms. And you can also write the system in terms of a first-order differential equation system. And we identified two types of inflation. We call this a type 1, where this is the initial condition, and inflation takes place here, along this cycle, not along the cycle, at this point in the cycle. Okay, these are different initial conditions on W, and then it's an initial condition in X, which is the field. W is that kinetic energy. Then you obtain this behavior. Okay. Type 2 means that for this initial condition, there's a movement, there's a curve in field space. Okay. So in this case, it's more tricky because we can get a generation of entropy perturbations, which feed the curvature perturbations. We have to be careful with that. So these are the corrections we have to take into account. But we found a region of parameter space that fits the data. And here we're talking about the 2013 Planck data. But it's okay. It's about okay. Yeah. And then later on, in a more recent paper, we looked at the non-Gaussianity in these multi-field models. And we found that it's within bounds. The FNL, it's always very small, independently of the shape. Okay, and then we looked with the master student at inflation in Reynolds syndrome. So we're assuming that we are living in the brain. There's an extra dimension where only gravity can propagate. Surely you know or heard about this. And different things that now there's a quadratic correction on the energy density. Okay, so I'm not going to bother you with this. All the equations of motion are the same because we are constraining matter to be on the brain. Yeah? So I'm skipping the details. Doesn't matter now. Let's look at the bounds. So this is for the same potential I looked at, yeah, for the single model in the paper. Okay, so we're looking at the same models, comparing the two in different setups. So one is the FRW, usual FRW. This is Reynolds syndrome. Okay, this is the same result we had before when you compare to the Planck 2013 data, and this is in the Reynolds syndrome. So the smaller lambda is. So this scale where the quadratic corrections come into play, then the worse it gets, as we expect. Okay? So you are doing this exercise, you are putting limits on this scale, on what lambda can be. Okay? Right. So yeah, to be honest, the first person to work on inflation with three forms was Cristiano Giovanni and friends, and it was interesting because they had this setup where they coupled the three form to the Newman tensor. It was interesting. So it's a question of playing a little bit with the indices and see what are the possible combinations and work out this model. They wrote it also in terms of the scalar field with these funny kinetic terms. Okay, in the theta, this is G lambda alpha beta, G alpha beta. And what they found out is that the curvature perturbation decays. So in their own words, a diverticity of linear perturbations is lost due to the non-minimum confidence. And this model, therefore, cannot explain the CMB observations. Okay? Yeah?
Do you have a ghost with that interaction?
Wait,
There's a non-linear coupling.
but you complain to Christian, yeah? Perhaps. Maybe they mentioned this in the paper. I don't know. Okay. Anyway, it's not viable. We agree with that, no? Okay. Then reheating and preheating. This was studied by Felici and friends. And what they do is to couple this reform to a scalar field. Yeah. And this is actually interesting. I think it's a very nice paper because they show that the reheating temperature takes this form and is 10 to the 5 times larger than the reheating temperature in a model like this. So R square inflation. Okay. And then you can look at the matter equation, which gives you how particles are produced, the exclusion of particles in the reheating model, and you obtain these coefficients in the matter equation. So you want this, especially Q, to be large. And this is easily obtained in this model. And on the other hand, there's, this lasts for longer. This resonance band lasts for longer because it decays as 1 over T, whereas in the standard scalar field, there's a power of 2 in this situation, in this expression. Okay, so it looks promising. I think there are things to do here. I mean, the actually mentioned that one has to study the back reaction on the inflation background field, and I think it would be interesting to couple with another 3 form. Since we are talking about 3 forms, maybe it makes more sense to couple with another 3 form than to a scalar field. Okay, that's what to do there. Dark energy, in this case, we are looking at how dark energy couples with dark matter. And there have been plenty of work on this. I and Tommy were one of the first to do this. And the thing here is that by introducing this coupling with dark matter, the potential that looks like this now is an effective coupling because of this form, this chi here. So this is the derivative of chi, so the potential will be inverted. And introducing this coupling slightly shifts this potential, this effective potential. Yeah? So you can have inflation even if you start with 0 kinetic energy. It's very interesting, with 0 potential, 0 kinetic energy. So, and then we have the density of perturbations, how do they evolve? There's something interesting here, is that there's a speed of sound, effective speed of sound here, which if it's negative, then it will lead to a large value of k. For very small scales, it will lead to a growth of perturbations. Yeah? So this will give either an imprint on the structure, or a signature, or then you exclude these models. Okay? But this is something interesting. So you see that for large values of k, small scales, there's a growth on the perturbations. Okay? I'll skip this now because I don't have so much time. But the other people looked at other different couplings, and they looked at mostly at the dynamical system. Yeah? And Marion, who's also here, but she also worked on this with people in the interior, and she looked at this coupling. And the idea here was to avoid the little sibling of the big rib. Yeah? So the case where h goes up in a finite time, where h dot does not go up. Okay? And with these couplings, well, some of them coming from this more general one, they do achieve that. They avoid this big rib singularity for the little sibling. Okay, Tommy Cavisto and Federico Urban looked at 3 form fields in order to generate magnetic fields. Yeah, and this is interesting. I'm going to read all of this. But the way they did this was by coupling the 3 form, actually the dual of the 3 form, so the vector, with the vector potential, the electromagnetic vector potential. And by doing this, we obtain a solution for the vector potential, the electromagnetic vector potential of this form. So if this gamma here is autonomous square is positive, then you ensure that you can have growing and decaying solutions. Yeah? And they do that. Well, they work out when can they obtain this gamma being autonomous square being positive, and it happens that for some region of parameter space, they can have indeed that this gamma square is positive. Then having this instability and this huge growth in the magnetic fields. Okay? And they have some plots. They show there's a region of parameter space so that they can achieve that. Okay? So, and that's the region of decay modes where they, in particular, they can have this growth in the magnetic fields, amplitude of the magnetic fields. Okay? I think this is interesting. And to finalize, I have 5 minutes maybe? Yeah. Okay, so then we're looking at schematic mechanism in this reform. And before I go there, I mentioned this work of David Morton and José Beltrán, but they look at the vector field, screening with the vector field. And in this, the starting point is this one. Yeah, so they have this action, and they obtain this equation of motion for the vector. And it looks very similar to the symmetron. And they obtain solutions that are very similar to the symmetron. So in particular, they take that inside a massive body, the field is at the minimum, and outside this body, very low dense regions, then there's a breaking of symmetry, and the field acquires one of those values. Okay, and this is very interesting. They obtain a profile for the field. There's 0 inside, and then it takes a value outside. And there's this thin shell where the field changes a little bit, but only this thin shell contributes to the interaction. Right. So what we did was to start from this point. We do look at the vector, so the dual of the three form, in order to compare with what they were, and we obtain a slightly different equation of motion. So I remind you that before the equation I showed you was a box vector, and not this gradient of a divergence of a vector. Okay, so it's slightly different. In our setup, we chose the potential and the coupling to be of this form. Okay, so again, we also obtain well, there's a minimum at b equals 0, with vector being 0, a value of 0, and when the derivative of the potential is 0. And in this case, we choose something slightly different. So we want to recover isotropy outside the massive body. So we decide that in the low density regions, we are here, at b equals 0, and in the high density regions, we are here. Okay, we are allowed to do this. Right? So, okay, I'm going to skip the details, but you find the solutions inside the body, in the intermediate region, or in the shell, and outside. Okay, so it doesn't matter. What matters is with the picture, and this is the profile we obtain. Okay. Inside, it's a constant. It's a constant value. It's not 0. It has some value in some direction, and then it decays to 0 outside the body. Okay, I think it's cooler. So you see that the streamlines of this vector, and this is a non-zero vector inside the body. Slightly changes in this thin shell, and then outside it's a dipole. Yeah, it's a dipole, but it's almost 0. Okay, so you have to imagine that there's a quick decay outside the body. Okay, so essentially that's it. We looked at the constraints on the parameters for this model, and of course demanding that there's a symmetry inside the sun, and there's no symmetry inside. There's a break of symmetry inside the sun, so that we have a vector, and then outside the sun there's a symmetry restored, so that b equals 0. Yeah, and then we have this constraint. Yeah, on this relation between the parameters, and then from the Cassini we obtain this low bound on u. Okay, and then in pictorial form, this is what you obtain. There's a region of parameter space, and this is all consistent. Okay, and I think that's it. It must be 2 minutes. Okay, so just summarizing. Three forms, we look at three forms as a possible candidate for dark energy and for inflation. And okay, we saw that the spectral index is consistent with observations, where n equals 60. The models, it's a models generated from Gaussianity, large value of non-Gaussianity, but some are within bounds. We looked at reheating and preheating, and saw, I didn't see that Felici saw that it seemed to be very efficient. And other aspect, it can generate magnetic fields, large enough magnetic fields. I think this is something under study. I think this is not the last word, but it looks promising. And there might be a signature on the growth of structure for very large scales. You know, for very large scale structures grow very quickly. And there's a new fish-4 screening solution. In this case, we have a dipole. You don't have no longer have this symmetron profile as we saw before, even for the vectors. So I stop here.
Any questions?
I'd just like to ask, I mean, I saw a plethora of different coupling lines, right, in terms of reheating, in terms of BCM. Can you say, are any of them derivable from, say, M theory? Or are they just pulled out of the air?
They are all phenomenological, as true. It's like this. In string theory, you do obtain three forms. You can obtain the potential for a three form, but they're usually quadratic potentials, which means that they're equivalent to a scalar field. you can immediately identify the relation, you know, if there's scalar field with a quadratic potential. So it's not so interesting.
Well, it depends on what you do, because, I mean, if you take the literal interpretation of M theory as a theory of brains, then the free form will couple with the fundamental objects in that theory. Then if you try to dimensionally reduce and compactify, the couplings will maybe look like this, maybe not. I'm just asking, is there been any effort to try and see what M theory would say for these couplings?
Then the answer is no. I thought that the best thing you could expect was a quadratic potential. If you tell me that, then I should have a look.
Baron?
For the growth of structure, did it take into account the preservation of the sequence or just the preservation of the
We took into account the perturbation in free form. So we look at the Newtonian limit, obviously.
Okay, I'm just asking because the equation you showed is everything the cap, so you have only delta n. So maybe you're taking large K or the...
I mean, using Newtonian approximation, then you substitute the perturbation in the field, and then everything is consistent.
More questions? No? Okay, let's thank us.